Okay, 10th grade, here we are, lesson number 3 about enthalpy and enthalpy change. We'll be building off both specific heat capacity and continuing to talk about energy and chemical reactions today. So here's the term for today. Please take a minute and draw this. It's a 2-pager. Okay, so we're working still on our first big idea here about conservation of energy. So that we have energy not being created or destroyed, and how that explains different chemical reactions. We should be adding to that as well today, as well from last class. Okay, so let's talk about specific heat capacity. So last class we talked about this, and we learned that it's the amount of energy it takes to raise 1 gram of a substance by 1 degree Celsius. So this can be pretty useful information. It can help us know how much energy is produced in a specific is used to make a specific temperature change of a certain substance. But if you're doing this and you change the mass, let's say you calculated Q for 5 grams of a substance, and then you were doing a new experiment or a new application of the chemistry later on, and you weren't going to use 5 grams, you were going to use 8 grams. You're going to use 10 grams. What would happen? Well, you know that it would increase, there'd be more energy required, but you wouldn't know directly how much to do the whole calculation all over again. So that's part of the reason why specific heat capacity in of itself is not as universally useful as enthalpy is. So enthalpy, also by capital H, is much more useful in terms of like multi-applications of this idea for energy and chemical reactions. It's the heat energy in a chemical reaction, hence the H. And while we can't often measure the heat energy directly, we can often measure delta H fairly directly, fairly easily. So the change in enthalpy is a much more useful calculation you're able to do. There you can figure out enthalpy per mole of a substance. So here's a formula for delta H. Okay, right here, how it relates to Q from this Q over here from heat capacity, and here's our Q here, moles, and delta H. So we also just change it as delta H equals Q over N. That works too. We need to have this information written down in your notes. Okay, so most of the time in the practice we're doing today, when you want to know about the energy of a reaction, at the end of a chemical reaction's equation is written out, you'll see where it says delta H and then some value. And that's showing you the energy of that reaction now. If it's positive value, that's an exothermic reaction. If it's negative value, it's an endothermic reaction. And usually it's measured in joules per mole or kilojoules per mole. So as I said earlier, it's really hard to measure enthalpy directly of the reactants and our products from an experimental apparatus, but it's a lot easier to tell the change in enthalpy. Remember, enthalpy is the heat energy from the reaction. So we look at this diagram here, this enthalpy graph. What type of reaction do we see here, and how do you know? So this is an exothermic reaction, and we know it's exothermic because the starting energy is higher than the ending energy, and energy was produced and left into the surroundings during that reaction. So if this is exothermic, what would an endothermic one look like? Well, an endothermic, it's taking in energy from the environment, so the starting energy would be lower and the ending energy would be higher. And this EA, we know what that is? That's the activation energy. We're talking about later. We talk about catalysts. What? Kuka, go ahead. Sorry guys, it's the puppy. Okay, so here's a really good diagram I like to help you kind of visualize and understand what enthalpy is in terms of a reaction. Okay, so if we have my total enthalpy of reaction, I have the enthalpy, the heat energy from the reactants and from the products. So the energy, what we talked about already, in potential energy in chemical reactions comes from the bonds between atoms. So the bond energies in the reactants and the bond energies in the products. The total enthalpy is this bond energy minus that bond energy. And it should be in a balance, right? If this is going to be bigger, they're going to have an exothermic reaction. If this is smaller, it's an endothermic reaction. Okay, so in an endothermic, I'm going to have the thermal energy coming in from the surroundings. If it's exothermic, I'll have energy coming out from towards the surroundings or from the reaction itself. It's a nice way to kind of visualize. You don't have to draw it, but if it's fun, helpful for you to keep track how this works, then please do. We'll be talking about bond enthalpy next lesson. Okay, this one you do have to draw, and these are our two graphs of energy or enthalpy in reactions, where we have an exothermic reaction and endothermic. So notice here exothermic was with high energy and it's going lower. And here's my delta H. It's negative because I've lost heat to the environment. Whereas here, endothermic, I'm going to be going from low and going high. My products are over here, and that's going to be positive delta H because I'm gaining heat from the environment. Okay? Be careful, it's easy to mix that up. I think I might have said it backwards earlier. So exothermic is negative because it's leaving, it's losing heat. Endothermic is positive because it's gaining heat from the surroundings. Okay, so to talk about enthalpy change, we need to use units. Those units actually depend on the mass used to calculate energy, or Q. So I think Nadine pointed out the fact that in the one formula I gave you guys last lesson, it was talking about using grams for mass. Some of those using kilograms. Either of those really are okay, and I didn't clarify that particularly well for you guys or at all last class. But what that means is it changes the units for your energy. So Q, if you do your mass in grams, then the enthalpy is going to be in joules. If you use kilograms, it's going to be in kilojoules. Just keep that in mind. Make a note of that in your formula sheet, guys. So the most way to kind of talk about enthalpy and talk about heat change in reactions is by talking about the units per mole. So how much energy per mole, and this is also called molar enthalpy. We'll be talking about that and calculating that as well today. So if you know molar enthalpy, then at the balance chemical equation, you can figure out exactly how much energy is produced by any one single part of a reaction. We're doing some practice calculations, breaking down reactions, figuring out how much energy we're getting from certain reactants or certain products. Okay, so look at this picture here. We have the alcohol burner versus a paraffin burner, and we're going to heat up water in a can, and there's a temperature change. Keep this visual in your mind, and we'll look at the next practice question. Okay, so we have a burner half filled with liquid heptane, so heptane C7H16. It's weighted put under a beaker containing 200 ml of water on a tripod, like that picture I just showed you. The temperature of the water was recorded, and the burner was lit. The water in the beaker was carefully stirred with a thermometer, and when the temperature was exactly 20 degrees, the flame was extinguished and the burner was reweighted. It has lost 0.5 grams of mass, and we should use those results to calculate the molar enthalpy change for the reaction. So this is where some of our stuff for our stoichiometry unit comes in. You have to remember how to talk about molar mass and moles of different compounds. Okay, so take a look at the information here. I have the balanced chemical equation, and we have delta H question mark. For 1 mole of heptane, you have 100 grams. I gave that to you here. And the formula mass for hydrogen 1, carbon 12. So you can use that to figure out what you need from there. So it's been a while since we did anything like this. So take a minute and give it a shot. Okay, so here is the final answer here. And this is a practice question example, so we'll go through it together. So you look here, our equation with enthalpy change or delta H. Kuga, don't mess with my iPad. Sorry guys, the puppy is touching the iPad. Okay, so the enthalpy change, or delta H, is the mass of the water, so heating up water, times the specific heat capacity, times the temperature change. This is just this formula rewritten in words. Okay, put the values in. I have 200 is a mass of water, 200 mils, 200 grams, same thing with water. 4.2 is the heat capacity of water, which you'd have to look up from a formula or be given to you. Most people in chemistry have that one memorized because water is a very common specific heat capacity to use. Anytime you're using a solution, we just use water's value for C. And then temperature change was 20 degrees. So my enthalpy change, doing that multiplication is 16,800 joules for 0.5 grams of heptane. So remember the final change in mass is 0.5 grams here, so I put 0.5 grams here. So then I'm going to do 16,800 joules for 0.5 grams, but I want to figure out how it is for 1 mole. I know 1 mole is 100 grams. So then I'm going to do 100 grams divided by 0.5 to get my conversion. So I actually only ended up getting 3,360 kilojoules per mole. That's what I get for that one. Okay, so let's look at calorimetry. Calorimetry is a way that we measure and examine experimentally the different energies of reactions. So the example we just looked at, that particular example, heating up the heptane, what are some possible sources of error in that kind of an experiment? Well, one could definitely be heat loss, right? If we have too much energy lost in the environment by not insulating our container, that's going to give us a very inaccurate temperature change. Temperature, the heat is not going to just be heating the water, it's going to be heating the surroundings as well. So in this particular image, they don't have any insulation around the metal can, and that's really not a well-designed experiment. Okay, so calorimetry in general is a process of measuring the amount of heat produced or absorbed during a chemical reaction. In this case, of course, it was the combustion of heptane was our reaction. And we can measure enthalpy change, or delta H, experimental by using calorimetry. It's a good system of experiments to do to measure this. So here's an example of a little bit better design. We have a calorimeter made of 2 styrofoam coffee cups, or polystyrene, that are layered to help give a really good insulation and keep whatever temperature change is happening, increase, decrease, whatever, keep it inside the cup. We have a stirrer to make sure that the heat temperature, the change in temperature is consistent throughout the entire vessel, not just one part of it getting hotter or colder. And of course a thermometer, and we're going to have some sort of lid on there to make sure the heat or cold doesn't escape. Okay? So we can use calorimetry for different kinds of reactions. We're going to look at different ones today as well as the next class. So here's some types. Dissolving a salt to make a solution. That's called enthalpy of solutions. So for example, sodium chloride plus water is going to give us sodium ions, chlorine ions, and water. That has an enthalpy change. We can do good acid-base neutralization reactions like sodium hydroxide plus hydrochloric acid gives sodium chloride and water. That's going to have an enthalpy change. We put metals and acid together, like we have hydrochloric acid again plus magnesium. It's going to give magnesium chloride plus hydrogen gas. And of course combustion reactions. Here's the combustion of methane. Remember, combustion always requires oxygen as one of the reactants and always produces carbon dioxide and water. So all of these, if I was going to do an experiment to figure out the enthalpy change in any of these kinds of reactions, they should all have certain things in common. To have a good experimental design and accurate data collection. What might those things be? Well, the apparatus is definitely one part of it. We have to have a sealed container like in this picture here. Multiple styrofoam cups is ideal. You want to be able to stir it without losing heat or adding heat. And you want to be able to try and trap all of the products of your reaction. So for example, in metals and acid, you're going to produce gas. You're going to produce hydrogen gas. You don't want to lose that. You want to try and keep it all contained as close to a closed system as possible. Okay, let's do a couple practice calculations and you'll be doing your own. So here's the first one. 350 grams of ethanol is heated using 22.3 kilojoules of energy. Remember, I'm using kilojoules and I have to use kilograms as my mass. Calculate the increase in temperature of the ethanol given that its specific heat capacity is 2.46 joules per degree Celsius per gram. So take a minute and try this one yourself. Okay, so we're going to be using this formula here, Q equals MC delta T, and my temperature is 25.9 degrees. Just substitute those values in, and that's an easy one. Number 3 here, another practice question, it's a little more complicated. Calculate the mass of butane gas would be needed to heat 724 centimeters cubed, or 724 milliliters, same thing, of water from an initial temperature of 7.44 degrees Celsius to 50.7 degrees Celsius. The thermochemical equation for the combustion of butane is, there's a balanced equation, and the delta H value. So I want to know the mass. So I have my delta H, and I have my, actually I can figure out the moles to figure out the energy from there. So you have to come back to our formula here for molar mass. Okay, which is why I have it on this page here. So if you don't remember these formulas, you may want to write them down in your notes. Okay, so here, triangle for molar mass. So of course, mass, molar mass, and moles. And if you want to figure out the molar mass in the periodic table, you take the relative atomic mass and add them up. So for example, if we're doing butane gas, which is C4H10 is our butane, I need to have the mass, atomic mass of carbon times 4 plus the atomic mass of hydrogen times 10 to get that number. So this is stuff we learned before. If you need help remembering how to do it, look in your notes, send me an email. I can recommend some stuff to help you guys out with that if you need it. So here's our answer. We're going to take our formula, Q equals MC delta T, and I have 724 is my mass, times 4.18, so the heat capacity of water, times my delta T change in temperature. That gave me 131 kilojoules, or 1.31 times 10 to the 5th joules. Then from this equation, balanced equation, I can tell that there's 2 moles of butane, like C4H10 is at 2 here. That means I have 2 moles for this equation. That's going to give me this number of kilojoules total per mole. Is 2 moles, gives me this many kilojoules of energy. So what I can do is I take 2 over that energy, because I have 2 in my equation, equals an unknown over 131. Because 131 is the kilojoules produced in the first part of my equation, the specific heat capacity equation. So I can solve for x, so 0.0456 moles. So what I basically did was just convert, let's figure out how many moles are produced, but actually what is this reaction versus what this kind of theoretically is the potential versus what actually happened. And then I'm going to take that mole value and I'm going to convert it to grams using this formula here. So the moles of butane, mass of butane is moles times molar mass. So here's my mass I calculated, 0.0456 times 58.14. That is the molar mass of butane, and that's 2.6 grams, 2.65 grams. Okay, so if you need more help with this, please feel free to reach out, okay? So you need to now do your practice questions. I have a worksheet here that has 10 questions, and you need to pick 5 of them to do. So here it is. We'll go over them this class. First one, again, just identifying reactions. There's different calculation questions, and we will go through them. I'll share the answers with you guys later, but you do at least 5 of them. You pick which 5 you want to do. So your homework is, of course, with your notes from a lesson, and then any 5 problems in that worksheet. Make sure you show your work, guys, okay? So I can give you feedback. All right, guys, so we'll get you to practice. Just give yourself some time and dive right in and do that practice questions, okay? All right, take care.